Hey guys, so this video is going to basically talk about empirical and molecular formulas. So let's just quickly define them. Empirical formulas represent the simplest whole number ratio, all right, of the atoms within a compound. All right, so this is kind of big thing there. So the simplest whole number ratio, while molecular formula is the true, or I guess the real ratios of the atoms in a compound. All right. And so these are really important, especially when we're looking at analytical and experimental data. Oftentimes, they're given to us in an empirical form, and we just have to do some little math here and there just to figure out what's the molecular formula. All right, so let's just kind of give some examples between empirical and molecular. All right, so empirical formulas, once again I said there are simplest whole number ratios. So like, for example, CH, this is an empirical formula. Let's see, C2H3, empirical formula. All right, simplest whole number ratios. Our molecular formulas, it's just a real thing. It could be anything. So like, for example, we have benzene. All right, so this is the molecular formula for benzene. That's the formula. If you want to know what's the empirical formula for benzene, you want the simplest whole number ratio between the carbon and the hydrogen. And so in this case, the empirical formula for benzene will simply be CH, okay? There are times that maybe the empirical formula and molecular formula are the same. So for example, CO2, that's the molecular formula for carbon dioxide. This is also the empirical formula of CO2. All right, so if the formula turns out to be also empirical, it's so as well. Here's another example. Sorry. So here is another example. So we have, like, for example, we have C5H10O5, sorry. So here, this is your sugar ribose. All right, this is the molecular formula for ribose. If you want to know what's the empirical formula, it's going to be, CH2O. All right, and so if you notice, this is the simplest whole number ratio. How we did that, we divided each one of the subscripts by 5. You get C1H2O1. Now, if you're given a percent composition of a particular compound of each of the individual elements, you could actually mathematically figure out the empirical formula for that compound. So like, here's an example problem. What is the empirical formula of a compound that contains 38.7% carbon, 9.62% hydrogen, and 51.6% oxygen? So what you want to do, first you want to change each of the percentages to grams. And the way that we could do this, so if they give you a problem, all of the percentages, you could roughly assume, well, all of them together, added together, are 100%. Well, let's just say if I have 100 grams of this sample, all right? Well, if you have 100 grams of the sample, then you could simply just change each of them into grams. So we could say that we have 38.7 grams of carbon. We could say that we have 9.62 grams of hydrogen, and then we could also say that we have 51.6 grams of oxygen, okay? Now, the next thing you want to do is convert each of these grams to moles, all right? And so we know that for carbon, for every 1 mole of carbon, there is 12.01 grams of carbon. All right, you plug that into the calculator and you get 3.22 moles of carbon. We know that for every 1 mole of hydrogen, we have 1.008 grams of hydrogen. Okay, and you plug that into the calculator, you get 9.52 moles of hydrogen. And then last, For oxygen, you have 51.6 grams of oxygen, so we know that for every 1 mole of oxygen, it is 16.00 grams of oxygen. You plug this into the calculator and you get 3.22 moles of oxygen. Now, we have moles. We know moles is really just a counting unit, all right? And so what you want to do, we want to change these decimals into whole numbers because that's how they're written in a chemical formula. So to do that, we typically want to change the smallest number to 1. How do we do that? Well, you divide by the smallest number. And why do we do that? If you find the smallest number and we make it to 1, then all the numbers that's larger than it's going to be the ratio of the smallest number. So like for example, when we look at this instance here, we see that the smallest number of all these 3 mole answers is 3.22. All right, and we have it twice here, so it kind of works out well. So what you want to do in this case is that you're going to take 3.22. Whoa, wrong type of utensil. Sorry. All right, so 3.22. You're going to divide them by both. So this case, 3.22 divided by 3.22 is 1. Here we do the same thing here. It's going to be 1. 9.52 divided by 3.22, and it's roughly really close to 2. Okay. Now that we have these numbers here, we could now figure out what's the empirical formula. So since this 1 is associated to carbon, this 2 is associated to hydrogen, this 1 is associated to oxygen. So our empirical formula for this question is C1H2O1. All right, and we know that we never really write the 1, so CH2O, and that's our answer. So now we're going to look at another example problem. So here's another example problem. So this question states, what is the empirical formula of a compound which consists of 89.14% gold and 10.80% oxygen? So once again, just like the last problem, you could rightly assume that you have 100 grams because this equals out to 100%. So it just makes this conversion really just kind of easy. So we have 89.14 grams of gold and then you have 10.80 grams of oxygen. All right, now your very first step, you want to convert this to moles. All right, so we know from the periodic table for every 1 mole of gold, you have 107.87 grams of gold. You put this in the calculator, you get 0.45 moles of gold. Okay, do the same thing for oxygen. So we know that for every 1 mole of oxygen, there's 16.00 grams of oxygen. You plug this in the calculator and you get 0.675 moles of oxygen. So just like the last problem, you want to divide by the smallest whole number because you want to know what's the ratio of every other element compared to the smallest mole number, okay? And so in this case, our smallest number here is our 0.45. So we're going to divide it by 0.45. We'll divide this by 0.45 as well. Now, if you notice, you plug this in the calculator, this will be 1, but this number will actually be 1.5. Now, you may be tempted to round, but you really can't because, once again, these are just ratios of one another, okay? So here we're saying that there are 1.5 times more oxygens than there are gold. So you can't round this to 2 because if you round it to 2, then you change the overall ratio. So we need the ratios to remain the same. So what we're going to do is multiply it by another number that's going to get this ratio to be a whole number. And if you notice, since because it's 0.5, I mean, anything that ends with a 0.5, you can multiply it by 2. So if you multiply this by 2, then we get 3. What you do to 1, you do to the rest. And so you have to multiply this by 2, and we get 2 here. So here are our subscripts to our chemical formula. So our answer in this case would be AU2O3. And that's our answer.